If you're watching this, congrats on making it to 1.5. Of course, you're going to be taking notes on this. So make sure you have this 1.5 worksheet. Thanks for stopping in. What's happening here? The same sequence is shown in both a table and in graph. So that's nice. We don't have to create anything necessarily. However, on the table, we have to show where the rate of change is in the sequence, then draw on the graph where we see the rate of change. Okay, so the rate of change, sometimes called the slope, is going to measure two things. It's going to measure the change in f of n, which as you can see here is just going to be adding 3. And it's also going to measure the change in n. If this looks like a triangle, that's good. If it looks like a Hershey kiss, you might be hungry. But this is measuring the change of if you were moving forward, what's changing. So the change in n is just adding 1. So this is consistent the whole way through. If I keep this pattern going, I'm always adding 3 for every time I add 1 to n. I would get in the habit of drawing these little arrows, drawing the arithmetic on the side, making sure that the changes are consistent and that it's not multiplying like a geometric sequence would. So for this, our rate of change is again, the change in f of n divided by the change in n. You might also call this rise over run, which we'll see in the graph shortly. But for this, we're just going to say it's +3 over +1. Do you think we could change this? Awesome person watching this. Do you think this could be simplified? Because it can. Changing it to +3 is good. But if you're a fan of using rise and run, maybe hold on to the 3 and the 1. Okay. So far we did this with the table. That's done. Let's switch up the color. If we're switching to the graph now, we're showing how this rate of change occurs. Okay, so pick any point. You can pick this or this or this, but you want to try and measure how it's going from this point to that point. First, I'm going to show vertically. So to get on its level, get on my level, how many units up does this have to go to get on this point's level? What do you think? Well, it started at 0, 1, 2, 3 hops. So it went vertically up 3. We call this our rise. The run, however, goes to the right, just 1 unit. Run, 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 run. Kurt Vile just did a cover of that Velvet Underground song, but our run in this case is 1. So lo and behold, we see the same numbers. Notice we can also refer to our rate of change as the rise over the run. We did +3 divided with +1. Lo and behold, same answer as before, but now in the graph form. What do you think? Could you have also taken this approach, doing the run first and then the rise? Would that work? You betcha, Red Rider. The order doesn't necessarily matter. Personally, I rise first and then run. But as you can see, this is consistent for all of these points. If we were marking from one point to the next point, it's always going up 3 and then over 1. So there you go for that. I won't show the table rate of change for this, but something you should note is that if the line's going down and to the right, and we're getting our rate of change, here we can still say that our run is going to be +1, but how do you think we should talk about our rise? Or is it really a rise? What do you think? You would actually want to think of this rise as -2. So how does that change anything? We still want our rise over our run. We still want to simplify it. So this could actually just be -2 as our rate of change. So be careful if your line's going down and to the right, your total rate of change should be negative. So make sure that happens. There's a lot to do for this sequence. We're being asked to create the recursive equation, which again asks us to find what f of 1 is, and then also talk about how it continues. So we'll get to that shortly. The explicit, again, recall that we could plug in any number for t and get the outcome in the sequence. So this is starting at 2 and it's jumping to 4. So we could say this is +2, but is it consistently +2? No, it's not. So if we look closely, it's really just taking the number that was here. And how do you think it's moving forward? It's not just adding 2 over and over. What do you think? Hopefully you're saying it's multiplying by 2 over and over. So how does this change things? Well, for the recursive, we could still start at 2 because that's right here. It's the first term. Just literally copy and paste it, write it again. But since we're now moving towards the function notation, recall we can still use words. We can still say that it's the previous times 2 equals the current. As we move towards function notation, we introduced how previous can now be expressed as f parentheses t minus 1, assuming you're working with the t variable, and then still multiply by 2. Current is still referencing f of t. So notice that we kind of use previous to talk about all this seen here. We still multiplied by 2. Current, we now refer to that as f of t, sometimes f of n, sometimes f of x, but I'm just sticking with the variable of t here, so I hope that's okay with you. Capiche? We saw in the 1-3 activity that this is going to continue growing, but it starts with 2. And since it just keeps doubling over and over, it's multiplying with 2. And then what do you think? Since this is starting at the n equals 1 term, so the first term, what do you think that exponent's going to look like since it's 1 away from the 0 term? Hopefully you're saying n minus 1. Again, because it's 1 unit away from the 0 term. That's a really big thing. So take a moment, try graphing this. So this is what this graph would look like. So what happened? Recall that the y-axis goes from down to up, the x-axis goes from left to right. I spaced out my x-axis in increments of, for every 2 blocks, it's only 1 plus 1. So this gives me a little bit more variety with how the curve actually goes, and it's not all tight together. My y-axis, I put in increments of 2. We said that when x is 1, the outcome's 2, and then 4, and then 8, and then 16. And if you wanted to get the 5th term, it's 32. If you even went backwards to the 0 term, it's just 1. So I have that denoted here. Take a moment, copy this if you need it. I think it is helpful for the next few problems. Does this look familiar? Do you want to try this? It's a day 1 problem. So chances are you might need an exponent in your explicit that has n minus 1. Do you want to pause the video? You want to try this? If you want to, go for it. If not, sit tight. I'll explain some things. So what did I do first? I looked at the pattern. I realized this is day 1. That soon becomes something of importance. I counted 1, 2, 3, 4, 5, 6 dots. I then noticed that over here, really just took the same thing and just had 2 versions of it. Notice domino of 6 and 6. This has even more. I think grouping in increments of 6 is a good move. If you think it helps, do it. Nothing wrong with that. So I noticed 6 jumps to 12, 12 jumps to 24. So I knew that no matter what in my recursive, I was starting with 6. We've already seen doubling as far as this goes. So the current was equal to the previous times 2, and we use this function notation for the recursive. Boom. For explicit, what happened here? No matter what, we're starting with 6. I was hinting that your exponent's n minus 1, because remember, this is talking about minute one or day one. So anytime that happens, you have to give respect that you're 1 away from 0. And since this kept doubling, you just multiply it by 2 over and over. Capiche? For the graph, I scaled this accordingly. I have 4 blocks to represent 1 unit on the x-axis. I'm allowed to do this because I'm evenly spacing these numbers out. And for the y-axis, for every 3 units, so count it 1, 2, 3, I'm making it 6. So I did that up and up. The pattern was already done for us. If you went back to the 0 term, you would notice that at 0 minutes, there's just 3 dots. If you're not convinced, draw up the pattern. I hope that this was good practice.